Anshu,
Yeah.
it seems that you have a much larger slide deck. I suggest that at some point you record for those slides and make that available.
I will do that, Ashin.
Yeah, because
I actually I had
anyway, this
no,
will be only a subset of that. So
right. I had planned to do that last night, but couldn't get the time. But I'll do it. Yeah.
yeah,
Okay. Anyway, so I mean, just quickly. So basically you have some control agents, right? You have activation functions, you have backpropagation, and optimization, as you can see, forms a very important, backbone of training neural networks, right? I mean, for convex cases and for non-convex cases as well. And we have some error bounds for both convex and non-convex problems, which we showed last year. That even for mean absolute error, there are error bounds. I mean, we can achieve an error bound and at least a lower bound of error, and is basically there is also an upper bound of the number of iterations to converge. Anyway, now optimization problems are hard, right? I mean, there are reinforcement learning kind of problems and other kind of problems as well. So generally, there are two types of optimization methods. One is a line search, and the other one is a trust region based methods. Now, for line search methods, in every iteration, so what we do is we find a direction towards the maximum descent in the optimization function and take a step in that direction with step length as the hyperparameter, right? Okay. So, however, I mean, in a problem which is typically visualized in this manner, I mean, we can also think of iterative methods which are called trust region based methods that define a region around any given point, okay, and in which the quadratic approximation of the objective function is valid. And then they search the region for minimizing that approximation. Okay, and that's the way for them to decide the next point in the iterative scheme. Okay, so one of the important benefits of such methods is that it is second order in nature, unlike many search methods which are actually first order approximation. And the method that we are proposing today, I'm going to talk about today, is also actually a line search method with the first order approximation, right? So what happens is it's based on the trust region policies are based on the effectiveness of the quadratic approximation. So if the approximation is excellent, then the search space is automatically increased or decreased, right? However, in a gradient descent or a stochastic gradient descent, which are pointwise line search methods, finding the optimal step size is always difficult, especially when the objective function is either non-quadratic or highly nonlinear. All right. So the optimization is a hard problem. It's a really hard problem, right? And there are several aspects. One is the learning rate. The other one is the overparameterization, so on and so forth. Which loss function are you going to choose? Is it really robust, and so on and so forth? Okay. So by landscape optimization, I'm referring to the trust region policy kind of methods. Okay. So as you can see in the slide itself, wherever relevant, I have kept the relevant papers that we have. So there is also this debate: is that should we be really worried about the local minima or try to find the global minima, right? Okay. I mean, it's important to escape the saddle points like the Pringles chip over here, right? But the obsession to find the global minima, it could sometimes lead us. In fact, there is a paper which shows that if you try to do that, right, then the network size explodes and the time to reach the global minima is also exponential. So people really do not care about global minima much, okay, when you are learning for the optimization problem. Okay, now I'm going to, so these are some of the caveats. I mean, these are a couple of slides which I always keep when we talk about deep learning over big data, right? Many a times leading to false meaningless inferences is because that the loss function is chosen is not appropriately robust enough, okay? All right, and there are some costs, and then this is a really hard optimization problem. What really happens here is that when we deal with problems in astronomy, particularly with objects from several catalogs, right? In this case, the stars and quasars, right? And when we want to make, now what people are trying to do is that they try to merge all the catalogs. So your feature space is continuously changing. So what is a good optimization or a classification paradigm for one particular catalog does not really hold good, right? Anyway, we solved that problem some time ago, but it's just an example of a very hard optimization problem, which is to detect the boundaries between stars and quasars. And this is, I mean, one of the things that, I mean, while training a neural network, the laptop got so heated up that, I mean, a collaborator of mine had to put it in his refrigerator, right? Okay. Anyway, so the idea is optimize, optimize, optimize. But how? You must have also noticed the way that the slide deck is prepared is that I have also tried wherever I could is to incorporate the basic reading material that for starters, right? I mean, for beginners as well. So, I mean, most of you do not need these GANs, but nonetheless. And then there are some benchmarking obsessions. I'm going to talk about it later, right? I mean, it's just listed over here. And I'm going to skip this slide as well, right? So the question is whether it's a local minima, global minima, do we escape saddle points? The answer is yes, right? Okay. So wherever pointwise approximation works, right? In convex, non-convex, sort of approximately convex landscapes, right? So there is this thing that we want to talk about, which is adder swarm. Okay. And in fact, this is the paper that I was talking about by Lekun and others, that in a multi-layer neural network, I mean, if you try to find the global minima, as the network size increases, the time to find the local global minima actually becomes exponential, right? So the idea is, if there is a loss function that is difficult to, compute, right? Is there a way to approximate it? Okay, using something else, I mean, using some other tools that we have, right? And that is what adder swarm talks about. Okay, all right. So it's a combination of Adam and particle swarm. All right, and this is the equivalence relation that we typically use in neural network training. Okay, where we can see that the error gradient, which is what you are supposed to compute because you have to eventually update the weights, right? So the error gradient can be approximately represented by this. Okay, all right. Where this delta y delta net is nothing but the derivative of the activation function. So all we require for this kind of approximation to work is that the activation function that you choose needs to be differentiable. That's all. Okay. Now, why? So the question is, why do I need to approximate the gradient, error gradient? The answer lies in several physical system problems. I mean, a good example being a Schrodinger equation, where your loss function is not a typical loss function. It's not a mean square error. It's not a cross entropy. It's not mean absolute error. It's nothing that you have seen so far. So what exactly is the loss? The loss is basically the difference between the left-hand side and the right-hand side. So it's like almost impossible to compute. Imagine some other very hard partial differential equations. The kind of equations that we see in ocean waves, right? I mean, those are irregular loss types. All right. So I mean, sometimes you can't even differentiate because the solution itself, right? The left-hand difference between the left-hand side and the right-hand side, the solution itself is weakly differentiable. It's not even defined on the Hilbert space. So these are some of the, at the same time, the kind of loss functions that we typically use, like mean square error, binary cross entropy, or even mean absolute error, right? Where you have difficulty in computing a derivative at a particular point, right? So you sort of require a gradient approximation. So these are some of the points at the surface which led us to, think of a method which we could use to approximate the gradient. Okay, all right. So the control dynamics is the following, roughly speaking, is that if we are near the local minima, right? And near the local minima, the swarm dynamics will help us converge. Away from the local minima, it's a simple gradient dynamics. Okay, whatever we do in gradient descent or stochastic gradient descent. So that's the mix. I must also tell you that trying to merge these swarm type methods with neural network type methods is not new. But what is new is that whoever attempted some sort of genetic algorithm kind of emulation of the gradient never really attempted to approximate the error gradient itself. So what they did was that they replaced the weight. So they have kept a particle for every weight. So imagine in an over-parameterized neural network, when you have millions and millions of weights, that many particles you have to deal with when you are handling into the swarm dynamics. And that becomes really, really cumbersome. Because the way swarms work is that there is one global best, right? And everybody needs to follow it. So you need to keep the population minimum. You need to keep the population fixed, and you don't want the population to go away. So this idea of G best is like this. So I'm going to skip this, right? So this is the Schrodinger solver, and the loss function is really the difference between the left-hand side and right-hand side, what we have been talking about. Okay, so one of the many motivations for us to attempt something like this, one was this Schrodinger equation. Okay, and there was another partial differential equation which we use in solving shallow water waves. I'll show it later. That's also what was another motivation. Okay, but our first experimental guinea pig was this Schrodinger differential equation, which we attempted to solve. Okay, and were successful to a particular extent for sort of different potentials. Okay, anyway, so this is typically the loss, and there needs to be some regularization of the boundary value problem. But this is what the swarm is, right? Now, typically, I'm going to skip all these equations and show you a very simple thing. So this is how a swarm is denoted. It's like this. I mean, we have all grown up in neighborhoods, right? Surrounded by neighbors, and then we had our parents, right? Who constantly, at least I was constantly reprimanded of not being able to live up with Sharma ji ki beti. Right? I mean, so my parents used to say, okay, so you look that neighbor's daughter, she's doing so well, right? What are you doing? So there is always this benchmark, right? So available somewhere over here that I have to sort of match. Now, in order to match the benchmark, I have to first improve. I mean, if I'm really bad, like I am really, right? I have to first, enhance my level. So in order to, get anywhere close to Sharma ji ki beti, or even in the context of Bits Pilani, right? I mean, it is Srinivasan ji ka beta, our own Ashwin Srinivasan, right? So it's like, in order to come anywhere close to Ashwin, you got to improve your level first, correct? So typically what happens is, I mean, I hope you can see this. So here I am, right? Okay. And so somewhere over here is the best performance of my neighbors. So that's the global best. So what I do is that here somewhere in this direction, this is my personal best. So, and my initial velocity is in this direction. So I need to be updating the velocity, and I also need to be updating my previous position, right? So you can think about this in a particle space, right? Where you are constantly updating the position. Why? The reason why you are constantly updating the position is because you are never happy with your current position. It's a striking analogy that you can find when you update the weights in a neural network. Why do we update the weights? Because we are not happy with the initial random position of the weights, and even after a few epochs, we are not happy with the value of the weights that we get, right? So what do? We update the weights. So this is sort of a metaphor that we used in our derivation of the gradient equivalence. So what I do is I move in this direction, and I find that I'm not good enough, even in my own standards. So I move in a direction parallel to this pi, right? So when I do that, the difference between this needs to be multiplied by a scalar, because you are moving in a direction parallel to this vector, right? Then what I find is that, oh, I'm not good enough in comparison with Sharma ji ki beti. So I need to move in the direction of Sharma ji ki beti, right? So in a direction parallel to Sharma ji ki beti. So then there is a difference between these two that you can easily compute, right? And multiply it by a scalar. Okay, so these two scalars, so you have these two scalars which turn out to be cognitive and social intelligence factors that need to be factored in as far as a swarm is concerned, right? Okay, so, and we sort of use this idea to solve a cooperative taxi ride problem. Anyway, so that is the basic condition of the swarm. But what really happens is sometimes, so typically these particle swarm kind of problems were first attempted to solve optimization problems, test optimization functions which do not admit of an analytical local minimum or a global minimum or maximum, right? So we use a population of particles, and one particle finds the best position to descend to, and everybody else follows it, right? Now, typically what happens with functions with many hills and valleys, right? You might get stuck. So whenever you get stuck, somebody came in and proposed a momentum term. So basically a momentum factor. There's a slight abuse of terms here that's going on, but that's not our fault, right? We did not propose the momentum particle swarm equation, but there is a momentum factor that was given to push the velocities, whenever your swarm gets stuck in a near a saddle point. Okay. Now we use this idea. Now, if you recall, in stochastic gradient descent also, if you think of, I'm trying to draw parallels between PSO and neural networks now. In stochastic gradient descent also, you kind of sometimes use a momentum term, right? Exactly for the same reason. Okay, so we borrow it from the neural network and we rewrite these PSO equations, the vanilla PSO equations, in the following manner that we have an exponentially average sort of a momentum, right? So this momentum term, which is the first term on the right-hand side, is as a convex combination, as a weighted combination of the momentum and the previous velocities. So what we are doing is that we are not discarding any of the previous velocities. But because this is a recursive kind of an expression, what you will see in the next slide is that there is, not in the next slide, I think this one, right? Sorry. What you will see is that the velocities which are farther away from the current position are given lesser weight because the beta is chosen between 0 and 1. Okay, all right. And in a typical swarm, there is this exploration and exploitation, correct? Okay, so this exploration and exploitation are given equal importance in the exponentially average momentum particle swarm optimization method. So when we started this, when we first proposed this method, neural network was not in our minds at all, right? We just wanted to solve multi-objective optimization problems. But it turned out later, as we kept on working, was that this could be extrapolated to neural networks as well. Okay, so this is typically another example that I could give, which is basically there are two people in two different boats, right? And there is a lake, and what happens there? Both of them are trying to catch a fish, and the fish is kind of naughty. It's sort of hiding in a very, very deep portion of the lake. So the idea is, in order to catch the fish, what you have to do is that you keep on scouring the depth of the lake, right? And you do that on a cooperative fashion, right? And I mean, I think the visualization is instructive enough that whenever, I mean, you and your friend are doing this, and each and every time you guys are measuring the depth of the lake and shouting to each other and communicating to each other, and when both of them agree that this is the maximum depth of the lake, the search stops. So that is typically the way particle swarm works, right? But as you can see here, right, or for that matter, any meta-heuristic algorithm, there are hyperparameters and parameters to tune. Okay, so the question at this point is that in a neural network setting where we already have a large number of parameters to handle, if we bring in particle swarm dynamics, aren't we complicating our life by having to handle more parameters? The answer is no. Okay, and why the answer is no lies in several theorems that we proved. Okay, what I can tell you, because the time is short, is that we kept each and every parameter under strict control and never played around with the values of any of the hyperparameters. Okay, all right, and we didn't need to. That is because of two things. One is that okay, let's go to this. I don't know why. Yes. So what you can see is here is that there are the cognitive and the social factors C1 and C2, right? So these are sort of hyperparameters that we really don't know. In a vanilla PSO, there's a von Neumann stability analysis which can be done to figure out what would be the optimal values of C1 and C2. Okay, what would be the optimal values of C1 and C2 so that the algorithm remains stable. So we kind of extended the same analysis. I think someone is trying to now. Okay, all right. So okay, so someone is okay. So that's the. So what was happening was, so we extended that same analysis to EMPSO, and we showed that if the sum of C1 and plus C2 is kept between 0 and 2, then the algorithm remains stable. And what we did was we kept C1 and C2 equal so that we give sort of an equal weightage to both exploration and exploitation phases of the swarm search, right? And R1 and R2 are random numbers, pseudo-random numbers drawn from a uniform distribution bounded between 0 and 1. That is pretty standard as far as particle swarm optimization is concerned. And we haven't really done anything about it to change it or we haven't really explored whether a better initialization works or not. Okay, so all right. So what we did was, so when we first thought of applying this to neural networks, so our first thought was to apply it to some standard test functions. So these are not typical test optimization functions in the sense that benchmark optimization functions are chosen, like Mishra-Bard or McCormick, nothing like that. These are test optimization functions. Okay, so we chose a few differentiable functions, we chose a few non-differentiable functions, and what we wanted to see was that whether the local minima or global minima can be efficiently found out by this method. Which method? By the method of gradient approximation. So we are not computing the gradient, we are using that gradient approximation formula, right? And using that approximation formula, we applied it on a bunch of different functions. I just showed you two here. Okay, and it turns out that near the minima, the approximation is pretty good. And as we move away from the minima, the approximation is not that good, as you can see here. Okay, which is fine with us, right? Because in neural networks, when you're trying to solve the optimization problem, you really care in the neighborhood of the local minima, right? Okay, so we did not really want PSO, the swarm dynamics, to dominate everywhere. We wanted the swarm dynamics to dominate near the minima. Everywhere else is just the gradient dynamics. So once we were able to, test it on differentiable and non-differentiable functions, we then thought, okay, let's now extrapolate this to differentiable and non-differentiable loss functions in neural networks. Okay, all right. And so the mind map is this. So this particular block actually tells us about the mind map, the entire process that went through, okay, over the last 1.5 years. Okay, so long story short, so the gradient dynamics and the swarm dynamics, they hunt in pairs for the kind of optimization problems that are required in classification. Okay, well, people are joining in now. Let me. Okay, well, these are okay. All right. So this is the first theorem, and do I have the time to show this? Because I just wanted to show one thing at least, which is because we had a lot of trouble convincing one referee, right? And that particular guy's concern, concern was that, well, there are too many confusing notations and it doesn't make sense to me and things like that. So what we did was to basically show in a very simplistic notational sense that how the two things, particle swarm and gradient descent, are coming together. Okay, so as I said earlier, that we update the particle positions because we are never happy with the present particle position. We update the weights because we are never happy with the present value of the weights, right? So there is some sort of metaphorical equivalence between the particles and the weights, correct? Okay, so if I really think about this, is that if you think of particle swarm optimization, it's this, right? It is xt plus 1. That is the updated position of the particle, right? Plus there is this inertia term, correct? And C1 R1, you know what C1 R1 is. There is this P best minus xt plus C2 R2 G best minus xt, right? Okay, all right. And so if you look at this, you take the difference between xt minus 1 and xt, and that is nothing but delta x, right? Okay, so this is the difference in the position that you really care about, and that is nothing but this guy, correct? Okay, now let's think about the plain vanilla gradient descent, right? And you just, as I said, as a metaphysical equivalence, I'm updating you, just w and omega, just w and x are just the dummy variable, so you can use any one interchangeably. So this is how you are doing the weight updates, right? Xt plus 1 equal to xt plus this hyperparameter, which is the learning rate, and then you have del f del x, correct? Okay, now, and from here what I can see is that it's very simple. The del f del x is nothing but xt plus 1 minus xt, the whole thing divided by this. So you call this equation 1, you call this equation 2, and what you do is that you substitute equation 1 into 2. If you do that, so this is what? What is this? This is nothing but your delta x, right? Or whichever way I'm defining this. Okay, so this is nothing but 1 by nu delta x. And what do I know about delta x? I know that delta x is this guy. Okay, so this is wvt plus c1r1 p best minus xt plus c2r2 g best minus xt. Okay, all right, and this whole thing over okay. All right, now there are some key things that we bring in here. It is well known that your search will terminate when your p best will be equal to g best, right? Because that's exactly how the swarm works. So you can replace the g best, right? Or you can replace the p best with the g best. So I can do this. So I can replace the p best with a g best, right? Okay, if I do that, you can see that I have g best minus xt in both places, and that will help me in combining these two terms. So I can write this as c1r1 plus c2r2 g best minus xt. Okay, what else? I mean, I can, just for mathematical equivalence or just for convenience, I can just assume that this learning rate eta is nothing but the inertia term, right? I mean, it doesn't really matter. Even if you don't do it, nothing will change, right? But there is this another thing that we need to know is that when the swarm moves, and let's say you have something like this, and the swarm, I mean, the population of the swarm moves, the moment you have actually reached the desired minima or the local minima point, right, the swarm will cease to move. It doesn't need to move any further, right? So what will happen is that at that point of time, the velocity will become 0, right? Okay, so that means that this goes away. Okay, so if that is the case, then what we have is that del f del x equal to c1r1 g best minus xt by nu, and so so 1 minus c1r1 plus c2r2 xt minus g best. Okay, and this we use later on in the Taylor series expansion, right, to update the error gradient weights. But this forms the crux of the idea. This actually helps us in figuring out how the error gradient can be approximated. And now let me take you back to, so I'm going to skip all this, right? This is a detailed derivation, okay? All right, and basically in the last 3 slides, whatever the content is shown in the last 3 slides, I have actually, worked it out, right? So for both the vanilla gradient descent version and as well as the stochastic gradient descent version with momentum term, right, we have been able to establish the equivalences, right? And we have been also able to extend this to non-differentiable cases. We just have to do a smoothing around the point of non-differentiability by using a shift parameter. Okay, so there is another theorem anyway. And this is typically a case of another sort of a extremely hard differential equation to solve, where you do not have a sense of these standard loss functions. So where you need to approximate the gradient. Okay. Anyway, so the idea is this: the neural update rule via ADA swarm is this delta E delta Y, which is exactly what we approximated by using the parameters of the swarm times the derivative of the activation function and the data. Okay, and this loss could be your mean square error, it could be binary cross entropy or cross entropy, it could be mean absolute error, it could be check loss, it could be anything in principle, right? Okay, and that gives us a handle on different kinds of loss functions. Okay, and so before actually attempting on benchmark data sets, what we did is we created a small data set, simulated data set with 3 classes, right? And we ran this. Okay, and you can see that after a certain number of epochs, the error gradient approximation is working pretty well, right? We have the gradient descent with the gradient calculation, actually calculated gradient, and the gradient descent with this particular formula that we have used. Okay, all right. We gained some confidence, and basically this is the code snippet where we actually call a bunch of other codes, and you can go to this GitHub repository to find out more about the code. Okay, I must admit that the code is not very clean at this point of time, but you get the sense anyway. Okay, all right. So, I mean, there are lots of other intuitions and inspirations that we have, but I am going to just skip and give you the big picture. So what's basically ADA-Swarm is? It's a theoretical equivalence to error gradient computation in neural nets. So this helps us, when you do this, this actually helps us to avoid the exploding number of particles in the swarm, okay, by using the other methods. So we really don't need to do that. And in fact, for all our experiments, we kept the swarm population constant fixed at 50, okay. As I already told you, the other hyperparameters, R1 and R2, we can't do anything, right? Unless we come up with a better initialization. C1 and C2, we proved the theorem to figure out a bound for setting C1 and C2, right? So what ADA-Swarm does is that the particle swarm dynamics is integrated with the backpropagation dynamics of deep neural networks. And this works on shallow as well as, you know, deep neural networks, narrow or wide neural networks as well, okay. And of course, I mean, in order to show anything that works, you have to, you know, benchmark your stuff. So we benchmarked it against all available state-of-the-art optimizers, which is starting with gradient descent, stochastic gradient descent with momentum, ADAM, ADAGRAD, AMSGRAD, ADADelta, DIFGRAD. DIFGRAD is actually relatively recent. I mean, it's a 2021 paper. And I think one of the authors of DIFGRAD is joining BITS Hyderabad campus, if I'm not mistaken. Okay, and so it all started with testing this stuff on a one-dimensional, non-analytical optimization problems, and then it snowballed into optimizing neural networks, right? Okay, and the idea is we were able to show so far, and we tested up to Schrodinger, that you give us any function, differentiable or not, we are able to approximate it by using the parameters of EMPSO. Not empirically, but theoretically, by using that gradient equivalence. I must also mention that when I say non-differentiable, what I mean is the function is differentiable with finitely many singularities. If a function is not differentiable anywhere, then this does not work. Okay? There are details about performance benchmarking that I would have liked to talk, but I just would tell you that we knew that the idea is sort of hard to digest. So we actually went ahead and tested it on any and every publicly benchmarked dataset that we could find, UCI, Kaggle, and everywhere. So we ended up testing it on 20 different datasets, out of which 15 are non-computer vision data, right? 2 class, 3 class, 4 class, and 5 are computer vision data, right? Because if you don't do computer vision, your paper doesn't get through, right? So all of that. Well, there are limitations because this is still line search. And as I mentioned, the approximation is not nearly as good away from the minima, right? It's first order method. So there are some subtleties, and there are ways to improve this by integrating with the Hamiltonian Markov chain, which we are thinking right now, which is how to make this first order method to a second order method, right? Okay. But I think, and that's basically what I want to do in future. Right. Okay. So this is Adventures from the Dancing Men from Sherlock Holmes. So I mean, other than dancing around, I mean, we just need to figure out a way to improve the order of approximation as well, so that we can use it in reinforcement learning kind of problems. Okay. So now there are a bunch of slides which I'm going to skip because, as I said, it was a slide deck, and there are some classic papers that I have listed out in the very end. Some of the classics are from the small data pattern recognition, non-deep learning papers, and these are some of my favorites in deep learning. And I would not want to finish my talk without acknowledging the 2 data scientists that India had produced, the greatest data scientists India had produced, Professor Malanabis and Professor Kosambi. And April is Mathematics and Statistics Awareness Month, and I have been thinking a lot about Mariam Mirzakhani, whom we lost at a very early age, right? And this is what I think. I mean, the Russians and the Jews are actually driving the theory of modern machine learning and deep learning as well. I mean, that's a sense that I get by skimming through a bunch of literatures. Okay, and these are my comrades in this struggle so far. I mean, I'm enriched by their hard work and the kind of value that they bring in over several projects that we have been thinking and we have been doing on deep learning, classification, regression, and other things, right? So the next stop would be to make Adaswarm more robust to, level noise, more robust to second-order approximations, more robust to landscape type of optimization problems, right? We're using some of the ideas that are already present in the literature. Okay, and that's it. Thank you.
Okay.
I had to rush through, but
Yep.
I think if there are questions,
I think I would suggest that you make a more leisurely slide deck with voiceover and put that on the.
come again, Ashwin. Come
I
again.
said that I would suggest you make a more leisurely slide deck with a voiceover and put that on the publicly available
Yeah, I'll do that.
site so that rather than the recording, because I think the recording is far too rushed. But
Yes.
are there anybody? Is there anybody who has any sort of?
In fact, the paper that got through, that was accepted just 2 days back. I have uploaded the paper and the supplementary file along with the presentation to the Google Drive already. So those of you who have access to the drive, you can easily read the paper, because there is a lot that I couldn't say. There is a lot I wanted to say that are in the paper. Actually, what we were also thinking is to make a sort of a visual demo of the whole process, and which we haven't been able to do so far, but we will be doing that. And as soon as we are done with that, we'll upload that as well.
Well, I'm sure. I don't know about the others, but I don't have sufficient background to understand more than a tiny fraction of what you said. But so any amount of additional examples and that sort of thing would be a great help. Are there any questions immediately?
I had one, if I may.
Sure.
And maybe I missed this, but could rules such as dropout be incorporated into this framework as well?
Yes, we have already done it. So I mean, there are some certain implementation issues that we have not been able to. I haven't been able to talk about, but yes, it could be, and it's already done. In fact, the particle dimension. There is another important thing that I should have talked about. The particle dimension. We employed batch training, right? So the particle dimension is restricted by the multiplication of the batch size times the number of classes for that particular classification problem. Okay. So to answer your question, yes.
All right. Thanks.
Anybody else? Any other questions?
It's a bit theoretically demanding, but I mean, I understand that. And so, I mean, you can just email me if you have additional questions.
So, Snanshu, I have a different kind of question about approximations in general, which I have not. I find that people dealing with approximations rarely want to do it that way for various reasons. Maybe the underlying theory is harder. But most of the time, when you're looking to approximate something, at least in machine learning, I have found that you don't actually care about the value. You're only caring about the ordering of things.
Right.
So you don't really need to approximate the thing at all. You just need to approximate the order of things, and that too, you don't care if your approximation is very bad or anything other than the top few guys.
Exactly,
but,
Ashwin.
but I find that nobody really wants to. So all of the optimization story is always about this is the loss function. We have to either optimize it, we have to approximate it so that we can get the lowest loss. Actually, you just want to get an estimate of the guy who's got the lowest loss. You don't really care what his loss is at all in many cases.
In a way, Ashwin, Adaswarm is doing that. But you know what the problem is? I mean, what you are saying, I agree completely. Okay, but you present that in public domain. Okay, you will be taken apart. So, I mean, the kind
possibly, I mean, somebody like you could present it better than me and wouldn't be taken apart if you look at rank order statistics rather than actually dealing with. So if you have a kind of statistical framework for your loss function and you're doing your estimates based on that, and you say that so you can do a reasonable job of it, but I mean,
you can, I agree. I mean, that is what some people are trying to do. I mean, resampling, right? Resampling is essentially that, right? I mean, so even I mean, to be honest with you, in this particular framework, I mean, I don't really require all the particles, simultaneously converging down to the minimum point. I really want a few, right? And I really don't care about others wherever they are.
So, yeah, so even in sort of deep networks, for example, I mean, I think Venkat raised the point about dropout, but I've always wondered whether do you really need the weights of all of these guys to be exactly where they are, or is it the case that for most of them they could be in any substantial large interval and not make any difference to the final result, which is why something like dropout anyway seems to
correct. I mean, yes.
So is it the case that I mean, is there stuff that goes on which says that okay, rather than estimating the weights, I'll just estimate the interval of the weights, and then that interval keeps shrinking and expanding as you sort of try to do the loss function. After that, when you're actually going to predict, you just randomly draw from that interval, and then you just
I mean, I think so, because typically then what you are essentially saying is that, I mean, that is exactly what I was indicating when I was talking about the second order approximation region around a particular point, right? So you typically have a bunch of weights, right? And you sort of require a few to be in an optimal position. And as long as the other weights are sort of embedded within a particular region, okay, defined by the topology of the network, you are fine.
Yeah. So what I'm saying is that rather than say that some particular guys have to be exactly some values, I'm saying that the whole thing becomes a business of narrowing and expanding intervals in which these weights are, and all you're doing is basically, or even you don't even have to narrow and expand the interval. Maybe you're just having a probability distribution over the values of those weights, and some of them have some small peak somewhere which you keep updating, and after a point you don't really care, in the sense that if some of these distributions change, it's not going to make any difference to the final answer, because the probability of class 1 is not going to change. I mean, the fact that class 1's probability is greater than class 2 is not going to change even if you jiggle a lot of these distributions in a substantial way. The class 1's probability will still be greater than class 2. So if you plan to, unless you plan to use the probability itself, it doesn't really make much of a difference. I don't know whether
yes. Actually, yeah, Tirtharaj is saying that Bayesian backpropagation exactly does that. I'm not sure how it works though, so he may probably tell more about it, right? But I mean,
so Tirtharaj, Bayesian backprop basically builds a probability distribution on weight values. Is that right?
Yeah, sure. It's
Yeah,
a parameter.
yeah, sort of, yeah.
That's a parameter of the Gaussian.
Right.
Yeah.
No,
So
but my point is this, that at some point, you know, you don't really need to know the exact distributions on those parameters to any great degree of precision. So you could have them as Gaussians, but does it really matter that the mean of that Gaussian is 2.1 versus 2.5? Probably not, I think, is my guess.
That I have to look at. I mean, I'm not sure. Mean
yeah,
may
neither
be
am I. But neither am I. But
Yes.
generally speaking, Ashwin, I think we agree. I mean, what you are saying is pretty much what is happening in Adoswarm as well. I mean, just that we don't know yet because we haven't looked at the probability distribution of the weights.
Well, so
But
I don't know whether you can do it, but I would think the idea of order rather than value, so using order
Yes.
statistics rather than value-based
correct.
optimization.
In fact, I was not obsessed with the value, actually, to be honest with you. I mean, it is because of the insistence of one particular referee that we had to do it. We had to show that, okay, at x is equal to 0, this is the analytical minima. At x is equal to 0, this is the approximate minima. We had to do that for all the loss functions as well. So because Ashwin, I think you should realize what you are saying is hard to digest as well. Right?
Not to me. I mean, for anybody who's done enough machine learning, we know that. I mean, most of us who spend our lives in actually doing this, we know that there's no point tweaking models beyond a certain point because it's not going to make any difference. Where in the end, it's the representation that matters. It's not the model, really. So that's my my position. I mean. Others will have that now. I can believe will be hard to digest for certain kinds of people, but actually, if any amount of machine learning will tell you that actually once all of the work is in the data, really, not in the models.
Okay. So I had a sort of quick comment that speaks to the broader point of that Ashwin is making. And sort of in the neuroscience community, there's this whole sort of genre of work that is motivated by the question of, well, in the brain, for example, how does credit assignment happen? As far as we can tell, there is no sign that there is sort of gradient descent going on, which requires significant amount of information flowing in the other direction. So there have been proposals where just with a modest but fairly noisy signal, people have been able to show performance that by and large does about as well as gradient descent. And so
yes, you're right. In fact, there is this thing called Langevin dynamics, right, which pretty much does that. I mean, what they actually show is that a stochastic gradient descent can be actually thought of as an Ito process. So what you are saying is correct, and that is actually one of the inspiring sources of this work.
Snehanshu,
Yep.
Navneet here from Pilani.
Yeah, hi Navneet. Yeah, hi Navneet.
Hi. I just, it's not a question, but just like there is a lot of work that's going on in mathematics on approximation theory, right? And I know a couple of guys who are deep into it. And so are we drawing anything from that work or?
Not much. Okay. Only when we are measuring the order of approximation. So if you are obsessed with what sort of order of approximation you are giving to your exact gradient, or how well are you able to approximate the error gradient if you do it the normal way, which is computing the error gradient, right? Okay. Other than that, see the mathematical approximation methods, like for example, the least square finite element methods or the Galerkin based methods, right? So these are local mesh methods. So what really happens is when you try to use this over a large landscape, these methods become really computationally expensive. So let me tell you that that example that I was showing, that the water wave partial differential equation, right?
Uh-huh.
So about a decade back, I wrote an LS-FEM method, which took me 3 days to run.
Okay.
That's because of the local mesh thing, because it's just because all the mathematical approximation methods are obsessed with the order of approximation.
Okay.
So anything between linear and quadratic, I mean, anything linear is not acceptable. It has to be at least superlinear, and better if it's quadratic.
Okay.
Right? So no free lunch, right? So if you are so obsessed with the accuracy of approximation, you will actually lose on the speed of convergence. Correct? So
yeah, I agree with you. But what I want to say is that if they are doing something on the values, right, we can definitely draw something for the order. So
yes, locally, yes.
Okay. So
I mean,
I'm not too much aware of that, but I know a couple of people, so probably I can connect you with them.
Sure. No, I also
right?
know people.
Yeah.
In fact, as I said in another live, that is what I was doing. I mean, like a decade back. So I am a numerical approximation. Used to be a numerical approximation guy. So I mean,
All right.
I know. I mean, so those are mostly finite element Galerkin-based methods, which are used on. Also remember, these are mostly on the kind of approximations people develop are only on laminar flows.
Okay.
Like they take a small section, they took a profile of the fluid, right? And they don't really do it. Like if you think of ocean waves, they do it separately for the deep water waves and separately for the shallow water waves.
Okay.
So they don't combine.
I have to go to another meeting, so I'll.
Are you okay, Shane? Go ahead.
Yeah.
Okay. Okay.
So okay. Thanks.
Yeah.
Okay. Thank you.
Okay. Okay. So I think Snehanshu, we can discuss it offline. I think we are all.
Yeah. Definitely. I'll also upload the video
Yeah, sure.
To the Google Drive, and then let Srinivas upload it to the YouTube channel.
Yeah.
So all right, thank you.
Yeah. Thank you, Snehanshu, for this nice talk. And we.
Snehanshu, it's a good talk. Yeah, we just enjoyed.
Thanks for the talk, Dr. Saha. Very nice.
Thank you, Dr. Srinivas. Thank you. Okay. All right, guys. Thank you.
Bye.
Thank you.